It's hot in Topeka. Okay, we are looking at Pascal's principle today with an example for fluids for the AP Physics 2 class. And before we start diving into Pascal's principle, what we're talking about, we need to set a ground rule, okay? And our ground rule will be this. All of the fluids we are going to be talking about and using in this class are incompressible. You cannot squish them, okay? And here's a water bottle I got, right? I can squeeze this water bottle down below, and notice how the water goes up in it, because I can't squish the water. I cannot pack that water into a tighter space. There is some amount of volume here of water, and I cannot decrease it. I can't decrease the amount of volume of that water. For air, I can compress air, right? But for fluids, like this water here, I can't do it, okay? If I squish it, it's gonna go up. That is our first ground rule. Yes, I recognize in real life at high pressure scenarios, you can compress fluids, okay? But for what we are gonna be talking about and doing, our fluids will be incompressible. This will allow us to use hydraulic systems pretty easily in this class, and to kind of look at how things should generally be working without having to get into the nitty gritty, like high pressure, weird, exoteric situations, or diving into some totally insane mathematics. Okay, so you can't squish fluids. They have a volume. Keep it. Because of this, we can now start talking about Pascal's principle. And the idea of Pascal's principle is that if an external pressure is applied to a fluid, then that pressure is increased by that amount all throughout the fluid. Okay, so the entire fluid increases by that pressure. So what we're talking about here is, imagine that I have a hose, okay? And inside this hose, it is filled with water. So let's fill the hose with water. I could never stay inside the lines in grade school. I just kind of drew all over the place. Okay, there it is. What we're talking about is that if we took a plunger or something, right? And first, we cannot actually compress these fluids, but if the water could come out the backside here, but if for some reason we were able to increase the pressure here, okay? So the pressure went up, then that means that on every single point throughout this system, okay, everywhere inside of here, the pressure has increased. The pressure is increasing uniformly everywhere inside a system. That is Pascal's principle. If the pressure increases in one spot, the pressure increases in all spot if that pressure increases due to some outside force or pressure there. Okay, so that's an important thing to consider. A kind of weird side effect on this, and this is kind of a tangent there, but if you have a hanging chain, so here's a hanging chain. This forms what's known as a catenary, and normally you can look at these hanging chains by saying, oh look, there is there's some tension force in this chain, and if you increase the tension in one spot, the tension increases everywhere because of Newton's third law. Sometimes it's actually easier thinking about hanging chains as tubes of fluid, and instead of thinking about tensions, you instead think about pressures. It's kind of a weird thing to do that, but if you get into some real high-level mathematics, some advanced Newtonian theoretical physics, you might start doing that at some point. So just ta-da! But let's not talk about that anymore. Let's get back to the fluids ideas, okay? Because of this here, what we're actually able to say with Pascal's principle is that, if we increase the fluid here, or increase the pressure here, this is some pressure in, then as this fluid is coming out, this is the output pressure. And that pressure in and pressure out have to be the same. So this allows us to say that the pressure we put into the system is equal to the pressure we get out of the system. The pressure increases uniform everywhere. And if we think back to what we can define pressure as, we define pressure as a force per unit area. So we can say that the force we put into the system divided by the area of that input spot is going to equal the force we get out of the system divided by the cross-sectional area of that output. And we could just kind of rewrite this if we felt like it as saying that F out over F in, so we divided by F in, equals the cross-sectional area out divided by the area in. And this might initially just look like, like whatever, it's just an equation. We can just rearrange it. But in the world of mechanics, this equation right here actually has already been seen, especially F out over F in. This, if you recall, is actually an equation for mechanical advantage. This is what we use for levers and screws and pulleys and ramps. If you are getting a larger output force than your input force, then you are somehow using a machine or a simple machine to allow you to exert more force than you're inputting. And you normally do this through a ratio of something else. So for like in the case of a ramp, right? In the case of a ramp, what we're doing is we're saying, look, I could lift a box from the ground up to a shelf. I could go vertically upward, right? This is some delta H, and that's all I'd have to move. Or what I could do, if that box is really heavy, maybe it's in my best interest to build a ramp. Whoop. That's a weird looking ramp. Let's try that again. Build a ramp. And this ramp, I'm still going up some delta H, but I'm doing this over a much longer distance. I'm doing it over a much longer delta X. And because of that, it's easier to push an object up a ramp than it is to just lift it up. You could also do this for, if you're trying to apply torques to objects or to lift something. A common or a classic statement is, if you give me a place to stand, I shall lift the world. And the idea behind that is to use a lever. If here is planet Earth, and you have a long enough lever arm, whooshing, then if you push down over here with some input force, this is a pivot or a fulcrum, you are going to lift the Earth up with some output force. And what you're really applying here are torques. These are torques that are being applied. And because we know that torques equals R cross F, or RF sine theta, really what we're looking at is the ratio between the input distance, or the arm, and the output arm. And if you have a very, very long input arm here, a very, very long R1, even if you have a very small amount of input force, because you're just a human, you can't actually lift the Earth, unless you have this, you can get a large output force here. So we are just applying the idea of mechanical advantage, but this time we are doing it for fluids. So this is just a cool mechanical advantage equation that we see. And we can actually use this idea of mechanical advantage all the time. One of the ways that you may have been using it is to lift up a car. If you've got a hydraulic floor jack at home, these are the floor jacks where you put it underneath your car, and you've got a bar in the back that you kind of pump down, and and then it slowly lifts up your car, and you feel like you're pumping it a million times, and your car like slowly gets off the ground. That makes sense. You have a more input distance than output distance, mechanical advantage. But you can lift up a car. Like, you're just a little human. How can you do that? Well, we're using physics and mechanical advantage here. So let's actually dive into this problem here and just see how Pascal's principle applies into this scenario. What we have here on this floor jack and the way they're set up is there's normally some small input area here. So there is some area on this side, we'll call this the A in, that we apply a force to, F in. And every jack is set up a little bit different, but generally speaking, internally, there is some sort of piping system that goes to the output, and this output has a much larger cross-sectional area. This is like A out, and because it's pushing up on your car, this is the output force. And all through here, normally this is filled up with like some sort of fluid. Normally it's an oil, so it doesn't like cause any rust or corrosion, and it's easily refillable. And it keeps things well lubricated. So there's an oil on the inside of there, but it is some just incompressible fluid. So let's see how we can actually lift up a car here. We know the car has a mass of 1750 kilograms, so kind of a big car or a big truck. And we know that the input area is 0.015 meters. So this area up here is 0.015 meters. The output area over here is 0.246, and these should be meters squared. I don't know why those aren't meters squared. Those are areas. Get with it. Oh, no, it's a diameter. I apologize. It's 0.015 meters in diameter, and then it is 0.246 meters in diameter. So I apologize for that. So this little circle here has a diameter of that with an input force, and the circle on the right-hand side has a diameter of 0.246. Okay. What we need to figure out is how much force do we need to exert in order to raise the car? So what is our input force here? So let's just work through our mechanical advantage equation and solve this out. We know that we can say, looking above, F out over F in equals A out over A in. So if we take the reciprocals of that, we can quickly say that F in over F out equals, what would that be? Did I mess that up already? F in over F out, A in over A out. Yeah, so we got, that was weird. A in over A out there. So we just took the reciprocals there. So this is A in over A out. And then if we just multiply the F out over, nothing too crazy going on there. We see that the input force that we need here, F in, is equal to the output force we get multiplied by the ratio of the areas. So this is A in over A out. Now, we weren't explicitly given our output force here, but we know that we're trying to lift the car, which means that that output force needs to equal the weight of the car. And we know weight equals mg, mass times gravity. So what we can start saying here is that our input force is going to equal mass times gravity, mg, where this m is 1750, and then multiplied by this ratio of the areas. And the reason I'm not putting in any numbers yet is I want to show us something kind of cool here with the ratios of the areas. We know that since these are circular openings here, circular openings have areas of pi r squared, or you could say that's equal to pi times the quantity of d over 2 squared. Now, I don't really want to have to do this division of divide by 2, and I really don't want to have to carry this pi around. And the cool thing about this is I really don't have to. If I write this out, pi, and then I just put d in over 2 squared over pi d out over 2 squared, what I quickly see is that the pi's have just divided out, which is wonderful. If I took the 2 squared, that'd be a 4, but in the denominator, I have the same thing, 2 squared, and both those are in the denominator. So those 2's actually go away. So we can actually write this entire ratio here as just really being the ratio of the diameters squared. We could just say it's d in over d out squared. And that makes sense because if you took the ratio of the diameters, that's the same as the ratio of the radii, because diameters are just the radii multiplied by 2, and the ratio doesn't care about the multiplicative of it. It just says, here's the ratio comparing one to the other. So we can finally just say here that the input force that we truly do care about is just equal to mg, so 1750 kilograms times 9.8 meters per second due to gravity, times the quantity of the input, diameter, 0.015, divided by the output diameter, 0.246, and then we just square that sucker. So let's crunch this all through the calculator. 1750 times 9.8 gives us 17,150. And then let's just hold that quantity there and take care of this weird ratio. And I get as my final answer, taking everything through, of 63.76 newtons, which is somewhere around 12 pounds. So it's kind of a cool thing that, if you can lift 12 pounds, or rather push down with 12 pounds, you could lift up a car, assuming that we had these type of input areas, which means a small child could lift up a car, given a hydraulic jack. Some jacks are set up so that the areas might be a little different here, so you might have to exert more force, but they give you a longer lever arm that you can kind of screw in, so you can use that to pump, and that'll allow you to move a larger distance and lift the car up a little bit faster. So a really, really cool thing that we see here, just using mechanical advantage via Pascal's principle. The pressure in is the pressure out, and using that, we can do a whole bunch of things further on throughout this unit. In our next video, we're going to be taking a look at the idea of buoyancy and Archimedes' principle and trying to help objects float. But until then, until next time, this has been finished. Adios, and you all take it easy.